So one common type of problem that you see in a number of multivariable calculus classes will say something to the effect of the following. Find and classify all of the critical points of, and then you'll insert some kind of multivariable function. So first of all, this idea of a critical point basically means anywhere where the gradient equals 0. So you're looking for places where the gradient of your function at some kind of input, some specified input x and y that you're solving for, is equal to 0. And as I've talked about in the last couple videos, the reason you might want to do this is because you're hoping to maximize the function, or to maybe minimize the function. And now the second requirement of classifying those points, that's what the second derivative test is all about. Once you find something where the gradient equals 0, you want to be able to determine, is it a local maximum, is it a local minimum, or is it a saddle point? So let's go ahead and work through this example. The first thing we're going to need to do, if we're solving for when the gradient equals 0, and remember when we say equals 0, we really mean the 0 vector, but it's just a convenient way of putting it all on one line. We take both partial derivatives. So the partial derivative with respect to x is, well, this first term, when we take the derivative of 3x squared times y with respect to x, that 2 hops down, so we have 6 times x times y. Y cubed, well, y looks like a constant, so y cubed looks like a constant, minus 3x squared, so that 2 comes down, so we're subtracting off 6 times x, and then again, this 3y squared term, y looks like a constant, so everything here looks like a constant with 0 derivative, as far as the x direction is concerned. And we do partial of f with respect to y. Then, this first term looks like some sort of constant, 3x squared, x looks like a constant, so some kind of constant times y. So the whole thing looks like 3x squared. The second term, minus y cubed, looks like minus 3y squared when we take the derivative, minus 3y squared. And then this next term only has an x, so it looks like a constant as far as y is concerned. And then this last term, we take down the 2, because we're differentiating y squared, and you'll get negative 6y. Negative 6 times y. So when we are finding the critical points, the first step is to set both of these guys equal to 0. So this first one, when we do set it equal to 0, we can simplify a bit by factoring out 6x. So this really looks like 6x multiplied by y minus 1. And then that's what we're setting equal to 0. And what this equation tells us is that either it's the 6x term that equals 0, in which case that would mean x is equal to 0, or it's the case that y minus 1 equals 0, in which case that would mean that y equals 1. So at least one of these things has to be true. That's kind of the first requirement that we've found. Let me scroll down a little bit here. And for the second equation, when we set it equal to 0, it's not immediately straightforward how you would solve for this in a nice way in terms of x and y, but because we've already solved one, we can kind of plug them in and say, for example, if it was the case that x is equal to 0, and we kind of want to see what that turns our equation into, then we would have, well, 3x squared is nothing, that would be 0, and we'd just be left with negative 3y squared minus 6y is equal to 0. And that we can factor out a bit. So I'm going to factor out a negative 3y. So I'll factor out negative 3y, which means that first term just has a y remaining. And then that second term has a 2, a positive 2, since I factored out negative 3. So positive 2, and that equals 0. So what this whole situation would imply is that either negative 3y equals 0, which would mean y equals 0, or it would be the case that y plus 2 equals 0, which would mean that y is equal to negative 2. So that's the first situation where we plug in x equals 0. Now alternatively, there's the possibility that y equals 1. So we could say y equals 1. And what that gives us in the entire equation, we still have that 3x squared, because we're kind of solving for x now, 3x squared. And then the rest of it becomes, let's see, minus 3 times 1 squared, so minus 3. We're plugging in 1 for y, and then we subtract off 6, plugging in that 1 for y again. And that whole thing is equal to 3x squared, then minus 3 minus 6, so I'm subtracting off 9. So from here I can factor out a little bit, and this will be 3 multiplied by x squared minus 3. And what that implies then, since this whole thing has to equal 0, what that implies is that x squared minus 3 is equal to 0. So we have x is equal to plus or minus the square root of 3. And maybe I should kind of specify, these are distinct things that we found. One of them was in the circumstance where x equals 0, and then the other was what we found in the circumstance where y equals 1. So this gives us a grand total of 3 different critical points. Because in the first situation where x equals 0, the critical points that we have, well, both of them are going to have an x coordinate of 0 in them, x coordinate of 0, and the 2 corresponding y coordinates are 0 or negative 2. So you have 0 or negative 2. These are kind of 2 possibilities. And then there's another 2 possibilities here where if y is equal to 1, when y is equal to 1, we'll have x's positive or negative square root of 3. So we have positive square root of 3 and y equals 1, and then we have negative square root of 3 and y equals 1. So these are the critical points. Critical points, which basically means all partial derivatives are equal to 0. And then in the next video, I will classify each of these critical points using the second partial derivative test.